Horizontal point source arrays consist of two or more point sources coupled together in order to achieve coverage in SPL greater than that of a single enclosure. Arrayable point sources enable large arrays to be deployed quickly that are scalable to a particular venue size and SPL requirements. EAW developed the first truly one-box system on the market in the early 80s named the KF850. Before the KF850, most systems were modular with highs, mids, lows, and subs all assembled from separate enclosures. The setups were complex by today's standards and were plagued with interference as each of the modules interfered with others. The KF850 united all devices, the low, mid, and highs, into a single arrayable enclosure that could be time-aligned internally and deployed to cover a majority of audiences. KF850 solved many issues in arrayability and interference that were occurring at the time. It was only a partial answer to the overall problem, as overlap between adjacent enclosures still existed. Arrayable point sources solved some problems in the deployment of large-scale reinforcement systems, but also had some inherent problems. Comb filtering occurs when two sound sources are placed adjacent to one another. In order to achieve constant SPL between two horizontally arrayed point sources, they must overlap. This overlap introduced a point where we hear both point sources simultaneously, but arriving at different times, leading to destructive interference in comb filtering. Physical offset of components leads to significant comb filtering, as well as smearing of the impulse response. So at those points where loudspeakers overlap, the result is often less than ideal. The situation is usually worse in the vertical plane where components are typically further offset than the horizontal. Typical point source arrays can't be aimed or curved to cover room geometry, so SPL is less consistent, so louder in the front than in the back. Less coupling means 6 dB of attenuation per doubling of distance instead for most of the spectrum. Modern line arrays offer some distinct advantages compared with horizontally arrayed point sources, such as improved vertical pattern control, vertical coverage that matches the room or audience area, scalability, and a single coherent source. Two conditions are required for a line source to be viable. Sources on the line should be placed less than a quarter wavelength apart. Length of a line array should be equal to or greater than 1/2 the wavelength of the lowest frequency over which directivity control is desired. To achieve optimal directivity, the array should be at least twice the length of the lowest wavelength that will be reproduced. The closer the sources are to each other, the higher in frequency they will couple and behave as a single coherent source. If sources are further than a quarter wavelength apart, they will act as separate sources and introduce phase anomalies in comb filtering at listening positions. Line arrays offer much closer source spacing than point source arrays. With traditional mechanically articulated arrays, it is nearly impossible to achieve a close enough spacing at high frequencies in order for the array to truly behave as a line source. As a result, only the low and mid-frequency components are behaving as line sources. For the high-frequency components, waveguides and horns are used to match the vertical beam width of the lows and mids to the high-frequency components. Essentially, it behaves like point sources at high frequencies. The modern-day line array system came onto the market during the early 90s. The benefits were real and the results were more than impressive. It completely changed the industry's approach to loudspeaker design, and manufacturers around the globe accepted it as the norm. So did the entertainment industry. The line array solved a huge problem in professional loudspeaker design by making the collective of sources in an array behave as one. Vertical columns of identical modules were designed that would have all devices placed within less than a quarter wavelength of separation over their respective operating bandwidths using various methods and waveguides. Suddenly, coherency became the new norm and product designs followed. The line array was not without its drawbacks, though. The coherent source was only coherent onto itself. Place a single column on the left and on the right, and you would maintain a coherent wavefront. But once you introduce supplemental arrays to the design, you introduce interference back into the overall system structure, even though each individual column may be operating coherently. Line arrays need to provide coverage to both the far and near field. Mechanical splay and curvature in the array is required. When side or outfill arrays are required for horizontal coverage, this curvature forces the arrays to be physically offset, introducing all the disadvantages discussed earlier with offset point sources. Comb filtering is caused by time arrival differences from each array. Adaptive systems combine the benefits of horizontally arrayed point sources, line arrays, and column arrays. They satisfy line array spacing across the entire audible range while providing consistent behavior at the low frequency, mid frequency, and high frequency. The arrays hang straight with no splay angles. Anya and Anna deploy physically in a barrel-shaped arrangement. Anya arrays in 60-degree segments, Anna in 90. Each module has discrete control, AMP and DSP, for every driver in the system. The images here show a single array from the same position producing varying coverage patterns based on which levels of seating are included in the acoustic model. Vertical coverage is not determined by splay angles or physically adjusting arrays. Coverage is determined 100% through software with a few mouse clicks. Horizontal coverage is fixed, but complex and asymmetrical vertical patterns can be created. A single cabinet is capable of 180 degrees of vertical coverage. Vertical coverage is determined by the relative locations of the arrays and audience planes in the control software Resolution. This allows an optimized vertical coverage pattern to be automatically calculated for every venue. This also allows different vertical coverage patterns to be produced in seconds with a few clicks of the mouse. For example, if a venue does not sell balcony seats for a particular event, the coverage can be adjusted to omit the balcony seating, and the entire output of the array will be directed to the seats that remain. Individual cabinets in the array will not need to be muted, and 100% of the system will always be utilized. Taking this concept into the audio world, these images show the same venue. The first image shows coverage using 8 cabinets of a traditional line array system. The contour lines represent 3 dB level changes. This system covers the room consistently, but variations in the coverage are apparent. The second image shows 8 Anya covering the same venue. The contour lines here essentially overlay the audience geometry. Because of adaptive product source density and ability to produce the ideal vertical coverage pattern for the venue, traditional line arrays simply can't match their performance. For virtually any application, fewer adaptive modules are needed to achieve equivalent output and coverage when compared to traditional line arrays. Typically, vertical coverage needs dictate the number of cabinets in the array. Sources need to be pointed towards the area where audio coverage is needed. This is exaggerated the closer the arrays are to the audience areas. With adaptive arrays, the number of cabinets is primarily determined by output needs. Since a single cabinet is capable of 180 degrees of coverage on its own, the system operator or designer can simply add modules until the desired SPL is achieved. This directly translates to reduced array weights, easier to manage sightlines, and a minimal visual impact. The images you see compare an array of 4 Anna versus 8 of a similarly sized traditional line array. Despite utilizing half as many cabinets, the Anna array produces higher SPL, is more consistent, and boasts lower overall weight. Comparing the control and directivity of lows, mids, and highs, reading left to right, between a traditional articulating line array and an adaptive array, you can see there are benefits throughout every frequency band, even with a shorter array. Digitally steered column loudspeakers direct vertical coverage by delaying drivers instead of physically offsetting them. This requires discrete AMP and DSP control of each driver in the column. A line array's high degree of directivity control makes it particularly well suited for use in highly reverberant spaces, where it is imperative that sound be directed to the audience areas only and not excite other reflective surfaces. This helps to maximize clarity in spaces with challenging room acoustics. The length of a line array should be approximately twice as long as the wavelength of the frequency we are trying to control. As the length of the line source increases, as will vertical directivity. Let's look at some examples of what happens as we increase the length of our line array. To direct energy from a line source, such as a column loudspeaker, it must be physically aimed at the intended listener. The same effect can be achieved through digital manipulation of our sources. If we have 2 sources, one on top of another, and delay the bottom source relative to the top, it is similar to physically offsetting that source. The result is summation, where the 2 sources arrive at the listener at the same time. When we add more sources to our line and have the ability to control each one individually, we can now start to form more complex directivity patterns. By digitally manipulating delay between each device, we can narrow, widen, and direct energy in any way we like. Let's take a look at a real-world example. Here we have 10 sources placed in a vertical line. In this example, we have no processing on these sources. The result is that they will sum coherently towards the center of the array. If we want to direct energy at the listener, we can do it one of 2 ways. The first is by physically offsetting each element in our array to achieve the appropriate pattern. In this configuration, physical offset of the loudspeakers introduces delay between sources, and summation will occur below the array. We can also do this digitally. By applying processing to each element individually, we can direct energy to where we want it. The result is nearly identical to our physical offset approach, but this approach is physically more compact and allows us to make changes to vertical directivity independent of position. Again, what makes adaptive so different? Why don't we call this a big steerable array? Why? Because there's so much more to adaptive. It's an evolving platform that's constantly updated with features such as self-healing, spatial EQ, multi-column arrays, and so on. How is all this achieved? Let's explore what's inside the box first.